Hello, let's work through the problems assigned out of section 5.3. So first up says use transformations to graph the function. So fundamentally, we begin with our graph of y equals 4 to the x. This is an exponential curve of the form a to the x, where a is positive, and more specifically, it's bigger than 1, which means that the curve basically looks like this. Okay, it will always go through the points 0, 1, and then it will go through the point 1, comma a, where a is the base. And since a is larger than 1, specifically in this case it's 4, that's how I know this point is higher than this one. This is at a height of 1, this is going to be at a height of a, which is our value 4 in this case. Okay, we could also plot some more points, like if x is 2, we have 16. That's just y equals 4 to the x. So if I want to plot y equals 4 to the x plus 3, okay, which I'll color code in green, that just means I need to shift everything up by 3 units. So look something like this. So now I'm at the point 0, comma 4. This is going to the point 1, comma 7. Up here would be 2, comma 19, etc. Okay. Determine the domain, range, horizontal asymptote, and y-intercept. So the domain for an exponential function is all real numbers, and adding 3 does not interfere with that, so that's all reals. Okay, the range, typically for an exponential function, the range is all positive numbers. Okay, so 4 to the x must be positive, which means 4 to the x plus 3 must be bigger than 3. So the range is all numbers larger than 3 and not including 3. Horizontal asymptote. Typically, an exponential curve has a horizontal asymptote of y equals 0, but this has been shifted up by 3, so the horizontal asymptote is y equals 3. Referring to our original picture, this exponential curve is going to approach this asymptote of y equals 0 as x goes to minus infinity, but it has been moved up by 3 units. And the y-intercept has already been given here. That's at y equals 4. Okay, moving on. So again, we want to graph this. So we just graphed on the previous slide, 4 to the x looks something like this. But observe that we are now doing 4 to the minus x. So replacing x with minus x is a horizontal reflection. So if I just want to graph y equals 4 to the minus x, I'm going to take the graph I just drew, but I'm going to reflect it horizontally. So it's going to look something like that. And then what we need to do is account for that minus 2. So I just take the graph I just had, and I move it down by 2 units, so it's going to look something like this. Okay, in terms of points, if I just started at 4 to the x, we would have the point 0, 1, and then we would have, for example, 1, 4, and we could have also negative 1, 1 fourth. Okay, note this is not the function we have at the end, this is just for the function 4 to the x. When I do this horizontal reflection, this remains 0, 1, but now I have 1, comma 1 fourth, and this is for the function 4 to the minus x, negative 1, 4. Now I take everything and I shift it down by 2 units. So I'd have negative 1, 2, I'd have 0, negative 1, or 1 and then 1/4 minus 2 is negative 7 fourths. Okay, I could also have, for example, negative 2, comma 14, etc. So we want to find the domain. So the domain of an exponential function is all real numbers. Reflecting it and shifting it up and down does not change that, so it's still all reals. Okay, the range. Now the range on the original exponential 4 to the x is all positive numbers. A horizontal reflection does not change that. A vertical one might, but a horizontal one doesn't. So when we have 4 to the minus x, the range is still all positive numbers, and then we shift it down by 2 units, so the range is all numbers bigger than negative 2. Okay. The horizontal asymptote, well, the original function had a horizontal asymptote of y equals 0. A horizontal reflection preserves that, it's just off to the right instead of to the left, but it's been shifted down by 2 units, so horizontal asymptote is y equals minus 2. And then the y-intercept has already been plotted. There it is. Okay, if you plug in x equals 0, you get 4 to the 0, which is 1, and 1 minus 2 is negative 1. Okay, now we just want to solve an exponential equation. So we have 4 to the 3x plus 1 is equal to 64. Now the thing to observe is that 64 is in fact 4 cubed. It's 4 times 4 is 16, and 16 times 4 is 64. Exponential functions are 1 to 1. What that means is if a to the x is equal to a to the y, then x must equal y. So 4 to the 3x plus 1 is equal to 4 to the third, which means the two exponents must be equal. And now I can solve this for x using techniques we've known for a long time. Subtract 1 from both sides and divide by 3. Similarly, I have 5 to the x cubed. Notice this is not the same thing as 5 to the x cubed. It's 5 to the x cubed. This is a common error. Parentheses really matter here. They're not written in the problem as given by the course, but the understanding is that x cubed is the exponent. It is not 5 to the x all cubed. It is 5 to the x cubed. Okay, so we have 5 to the x cubed equals 125 to the x. Now 125 is 5 cubed. So what we have is we have 5 to the x cubed is equal to 5 cubed to the x. And the reason these parentheses are so important is that on the right, this becomes the product of the two exponents. So I have 5 to the x cubed equals 5 to the 3x. Now I can use the fact that exponentials are 1 to 1 to claim that these two exponents must be the same. Okay? If I subtract the 3x to the other side, we'll get this, which can be factored as x times x squared minus 3 equals 0. And x squared minus 3 is the difference of two squares. So I can factor it as the difference of two squares, x minus root 3 and x plus root 3. And a product of three numbers is 0 exactly if one of them is 0. So x equals 0 is a solution, x equals root 3 is a solution, and x equals minus root 3 is also a solution. When dealing with exponential functions, we might want to be careful about domain. But remember, the domain of an exponential function is all real numbers, so there's not really anything to worry about here. What can happen in some problems is algebraic techniques might suggest solutions that are not actually in the domain of the original, so always keep that in mind. But for now, exponential expressions have domain of all real numbers, so there's no obstruction here. Okay, so again, we want 4 to the negative x plus 27 to equal 128 to the x. Now, 128 is not an obvious power of 4. However, 4 and 128 are both powers of 2. Namely, 4 is 2 squared, so I have 4 to the negative x plus 27. And 128, I just count these off on my fingers, so powers of 2, I have 2, 4, 8, 16, 32, 64, 128. That's the 7th power. So 128 is 2 to the 7th, and then I'm raising that to the x. Now I can use properties of exponents to say this is 2 to the 2 times negative x plus 27. This is now 2 to the 7 times x. I'll just go ahead and expand that out, negative 2x plus 54. And here I have 2 to the 7x. Exponentials are 1 to 1, which means the two exponents must be equal. I'll add 2x to both sides. Divide by 9 to get x is equal to 6. And we can double check that this is in the domain of both. Sure, plugging x equals 6 into either side here is not going to be an issue, so this was in fact a solution. Now our base is e, which doesn't really change anything. In fact, we directly have e to one number equals e to another, so since exponentials are 1 to 1, regardless of the base, as long as that base is positive, remember, we don't have negative numbers or 0 for the base of our exponential expressions. So since exponentials are 1 to 1, the two exponents must be equal. Okay, I'm going to go ahead and subtract 10x from both sides and divide by 9, negative 9. And again, exponentials domain is all real numbers, so this is in fact a genuine solution. All right, now we have a word problem. So a pane of glass obliterates 1% of the light passing through it. So the percent of P of light passing through n consecutive panes is given by the expression 100 times 0.99 to the n. Okay, so this is just given to us as a function. I like how the problem says it obliterates 1% of the light as if it's just gone. No, it's absorbed into the glass and converted into energy as heat, but fine. So what percent of light will pass through 5 panes? So the number of panes is 5, and we're just going to have to plug that in. For part B, the number of panes is 10, and we're just going to have to plug that in. So P of 5 is 100 times 0.99 to the 5th, and P of 10 is 100 times 0.99 to the 10th. Now, normally I don't like using a calculator to compute this sort of stuff. We have exact solutions in front of us, but for the sake of argument, I'm just going to go ahead and compute 100 times 0.99 to the 5th, and I get 95.10. And on the other hand, if I plug in n equals 10, we get 90.44. So if I put 5 consecutive panes of glass, I will have 95.1% of the light getting through. If I put 10 consecutive panes, it will be about 90.44% of the light getting through. The last part of this problem is a little vague in its phrasing. It just says, explain the meaning of 0.99. 0.99 simply means 99% of the light makes it through. Okay, if 1% of the light does not, 99% does make it through. So this 0.9 refers to how much light does pass through a single pane of glass. Okay. So if I have a pane of glass and a pane of glass and a pane of glass and a pane of glass, if I have, for example, 100 units of light, okay, only 99 out of 100 make it through. And now it goes through another pane, which means 99% of 99 makes it through, because 99 units attempt to make it through the second pane, so only 99% of that will make it through. Then 99% of that, etc. So notice we have consecutive multiplications of 99%, which is 0.99. And when I consecutively multiply it over and over again, I have 0.99 to a power. That's what 0.99 to the n is representing. Okay, another word problem. The price of a specific car that is X years old is modeled by a specific function. So this just tells me the number of years is 2 or the number of years is 7. Let's actually jump right to the last part before pulling out a calculator to do parts A and B. Okay, the meaning of the base 0.92 is that every year the car value is multiplied by 0.92. Okay, if I have 0.92 to the x, that represents multiply by 0.92 over and over and over again. In other words, the car loses 8% of its value every year. If it keeps 92% of its value, it loses 8%. Okay, otherwise, part A and part B are just plug and chug. So P of 2 is going to be 22,275 times 0.92 squared, and P of 7 is going to be 22,275 times 0.92 to the 7th. Okay, so if I just pull open a calculator to quickly compute these things, 22,275 times 0.92 squared is 18,853.56, 1885356. And on the other hand, if I use an exponent of 7, 1242603. 1242603. Okay, so unsurprisingly, the car loses value as time goes on, as we expect it will.